Oh my goodness, that happens every once in a while.
She had having a lot of blood clots, like the size of an orange. She lost blood.
Oh, guys, I don't see the. Oh, there it is. And of course, we'll cover basically what's in the gears, rotor chains, and belts. So gears, belts, and chains. What we'll look at. We'll look at the different types of gears, some terminology and nomenclature, force transmission, and gearboxes. And we're not going to do design. This PowerPoint was a lot. This is not my PowerPoint. Some of it is, and some of it's not. But this was one that was online that I pulled it off of, and they got into design gearboxes, which we're not going to do. But we need to understand what the gearbox is. What is the gearbox? Yeah, that's pretty much what it is. More than one gear is usually the way we would say it. So this is a pretty good video that we'll look at. In fact, I don't know why I didn't start. Let's see. It's hard to do on click because a lot of times when you do that, it'll advance the slide and start the video. So. Still doing it over the internet. I mean over the web. Let me go ahead and just show the video. And it probably won't have any skips in it. But I can get some speakers. Okay. Let me get the speakers out. Yes or no? Huh?
I can hear.
Surprised it came from the computer.
Well, we haven't got that figured out yet. For some reason, it won't find it. Still be just.
Probably has to be low.
Huh?
Is it low?
We're doing it on the wireless. Over. We'll try another thing. This has a lot of video fitted, unfortunately, the PowerPoint. I could go in and, so we'll come back and look at that later. It's pretty neat. What they do is the guy teaches ratios and how we can get the advantages and out of gears. But basically, gears are used to transfer power from a prime mover over to the load, right? I'm saying it can do several things. These are the types of gears we'll run into. Spur gears, helical gears, bevel gears, and worm gears, and then one thing that was left off here, off this list was, and the guy didn't have it in his PowerPoint, was a unit that we have called a ball gear, ball and screw gear. I get it in. Well, there's no balls to it. Worm gears are 2 gears, where ball screws actually use screws. This is basic gear of a spur gear. Now we have 2 terms we'll use. We'll have what we call the driver and the driven. Are we okay there? and you can see what happens when we go through. So one thing we have with gears that gives us a little problem in that if we go directly from the driver to the driven, notice what happens to the direction.
It's opposite.
Yeah, it changes directions. So I don't know if this is in this presentation. It's in the video with a gear that we call a secondary gear. We call an idler gear, which we can put in there that would make the driven and the driver go in the same direction. But we'll look at that. This is called a helical gear. Now, the biggest problem we have with spur gears is they're noisy. They make quite a bit of noise when they move. And a helical gear, notice it transfers the power more smoothly. So the biggest advantage of a helical gear is that it is quieter. So they're not as noisy as spur gears. Make sense? Then we have, and I did put then we have what we call a bevel gear. And of course, the bevel gear is usually used to do what? These can be spur gears, so notice these are straight bevel, and then this is what they call a spiral bevel. So what can we do with this? Well, we can change the rotation, right?
So can they go in the same direction?
Well, let's look at this. Look at this. So if you come over here and if this one's spinning this way, then this one's going to spin this way. So it's still going to reverse directions. Okay, y'all understand? This is the worm gear. We have one of these on our turret carousel over there. Has a worm gear on it. So what we do here is the advantage of here is we can do what? Yeah, or now, and of course these usually give us an extremely high torque. I don't know if you see these. There's a lot of jacks that use these. There's a lot of lifts that use these, or the guys that have a big old handle on the outside and they'll be spinning it. And of course the lift moves real slow. So gears are kind of like levers. If we go from, and that's exactly what there are. They're levers. So if we came over here and we had a lever, we have a device we call a fulcrum, right, which is what the lever rests against. And then what we do is we have a lever and we can play around with the lengths between the driver and the driven. So over here, this would be the driven. So it's going to move up, and this would be the driver. Right? You understand? Well, if we put the lever, if we put the fulcrum directly in the center, then what happens if I push down 100 pounds on this and we get 100 pounds on that? At the same speed. So there would be no mechanical advantage of that except to change directions. If we come over here and we start making this shorter or making this longer, it depends on where you put it. But what happens if we come over here and we push this down, I might require 100 pounds over here and I might be getting 30 pounds of lift over there. But what happens is this moves at a faster speed, depending on the ratio. So you can see this is going to cover a greater distance because this radius is different than that right there. Y'all understand that? Now what happens if we move it in the other direction? Well, if I make the long side over here and the small side over here, then we might be putting 100 pounds of push right there, but we might be getting 300 pounds right there. But what happens? Over here, it moves at a slower speed because of the radius, right? The length of the radius is changing. So it's just like something spinning. The further you get out, the faster you're actually rotating, right? Because you're covering more distance in less time. So this is the same distance. So the further we get out, then the faster we move. but it takes more force to move it. Well, so we have exactly the same principle on the gear, right? You understand? So if the gears are exactly the same size, then the output power and speed would be exactly the same as the input power or torque, what we call it. So torque is a twisting motion, right? You understand? Turning or a twisting motion. But here, if this is little and then this is large, then what's going to happen is this guy over here is going to slow it. It's going to run at a slower speed, but it's going to create more torque. And it's exactly like before. Here we can use different things to calculate. So right now we'll call this the driver, and we'll call this what? The driven. So what would happen is we can use different things. We could use the ratio between the diameter, or we could use the ratio between the radius. There's exactly the same. Or we could do the ratio of the circumference, or we could use the ratio of the teeth. That makes sense? And that gives you a ratio. So if this is 2 times the diameter of this one, then what would happen is this guy here would run twice the speed. I'm sorry, it would run 1/2 the speed, but it would create twice the torque. That makes sense? So the big gear runs smaller than the little gear. So a big gear would give you a torque multiplier, but it would give you a speed divider, right? You understand? If we did it the other way, if we turn this to the driver and this to the driven, then what's going to happen? It's going to be just opposite of this. So our speed ratio would double, but our torque would do what? Half, because we've changed the size of the radius. If the radius is smaller than the other side, it's going to run faster, but it's going to create less torque. So we can use gears to do one of two things. We can use it to increase speed, but we sacrifice torque, or we can use it to create torque, but we sacrifice speed. Y'all understand that? You're not changing the power. So power is equal to force times distance, right? You understand that? So if I've got so many horsepower over here, then if this was a perfect gear, I would get exactly the same horsepower over there. But it's going to be at a different watt. It's going to be at a different speed and a different torque. And that's what this guy right here explained. Let's see if it finally got downloaded. So what I did is I brought it over to my computer. That way it's not going through the... Pretty neat, right? It's a pretty good video. So, but you got to understand, this same video applies to all these different types of gears, whether they're bevel gears, whether they're spur gears, whether they're helical gears, whether they're worm gears, right? Understand that? That makes sense. Pretty okay. It's a pretty good video. I don't know if these others are play or not. So the one that's providing the torque, we call that the driver. The other one's called the driven. Another term is the pinion, and then the gear. That's 2 more terms we use to designate the gears. And then if we go through multiple gears, then we refer to those as gearboxes. So that's basically what your transmission is. But it automatically changes the ratio between the driven and the driver, right? Understand? So when you start off, you end up with what type of multiplier? When you stand in seal and hit the glass. You start off with a torque multiplier, right? Because anything that's sitting at rest wants to do what? Stay at rest. And as we accelerate up, you know, in the old days we had 3-speed transmissions. And then we moved 4-speed, and now basically all your transmissions are 5-speed. So I don't know if you ever get to 1-to-1. So you never actually get a true speed multiplier. But what they're doing is they're constantly changing the ratio between the what. So anything that's in motion wants to stay in motion. So that means we don't need as much torque while we're up to speed that we do when we're down, right? You understand? That's what an automatic transmission is doing. It's just changing the ratio between the what? The driver and the driven. Starts off with a real high torque. So, you know, most cars, you can let your foot off the gas and just the idling of the engine will cause that car to move. So it's moving the whole car, right? This is called an internal spur gear. Now, what's nice about these is the amount of space they take up, right? Y'all understand that? So the actual driver or driven is inside the spur, so we can either rotate this and cause this to rotate, or we can rotate this. This is used on a lot of earth moving equipment, shovels, where the whole unit is moving. This usually moves on this internal spur gear. This is what we have over there. We have a ball of screw gear. And there's really no mechanical advantage on the ball and screw because you notice the screws are fitting in the groove. So this is basically a one-to-one advantage. What we do here, though, is we convert rotary motion into what? Into linear motion. So these are used a lot on that. We can transfer thrust or torque with a high torque loads. So these guys work real well. Minimum internal friction. Now the disadvantage is because of that internal friction. A lot of times these things will backdrive. They'll actually gravity. If you're trying to do it to lift something and you let the weight on there, they'll have a tendency to backdrive on you. And of course these guys cost pretty expensive. But can you see how that thing works, ain't it? So what happens is that the balls come in one side depending on the direction. They move through the threads, and then they're automatically scooped up on the other side, and it's constantly now, yeah. Now you understand one thing we got to do, especially with these metal gears. We do have some Teflon gears that are considered to be, but those are low torque. They are basically considered to be self-lubricating. But your metal gears, this is metal against metal. Anytime we have metal against metal, we have some type of friction and we have some type of wear. So one thing we got to make sure we do with gears, of course, is we have to keep them lubricated, right? Out at USDL, they use something called gear lube. It's pretty thick stuff. And all the gearboxes, and that's one of the things they make sure they do is those gearboxes, they make sure they lubricate them. Another advantage we have with gears is any vibration that you have in the system is going to be transmitted through the system. There's actually no play in this. Another problem we have with gears is that if something happens and something stalls, you got enough horsepower out there, it can literally tear these things up. But we get really, really good torque. We get really good mechanical transfer. You know, if you keep them lubricated real well, they're going to give you a long life, but they will eventually wear. So we're going to move to a cheaper system. This is, by the way, the pitch of the gears, and the more torque you have to transfer, the bigger teeth you have to have. We refer to that as the pitch. So there's a lot to design in gears because the smaller you have, the easier the gears are going to be able, the teeth are going to be able to shear off, right? Understand? So what that means is if I'm going to a high torque application, then we're going to have to increase the pitch, right? You understand that? This is a slip clutch. This is what's in this thing. We use slip clutches to do what? Of course, your car's got one. If we didn't have a slip clutch, that means you couldn't stop your car. Because what would happen is those gears would do what? They would constantly stay engaged. So a clutch, what a clutch does for us is what? It allows us to engage and disengage the power transmission without stopping the prime movement. So if we didn't have that, you know, you slammed on your brakes, your engine would have to go dead because it could not turn, right? You understand? Either your brakes are going to give out or the motor's going to give out. Well, we have a clutch in there that's designed to do what? To deliberately slip. Of course, if you drive a straight shift, which is real fun, I couldn't drive one anymore. That was my preferred method for years. Now, what you do is you have what we call pressure plates. And what happens, how much pressure plates you put on those depends on how much you can actually. So we can use them not only to engage and disengage the prime mover without installing the prime mover, sometimes we can actually use it to the power transfer. If you ever driven a straight shift, you know, you don't just pop the clutch, right? What you do, you let it out real slow, and what that does is it gives you I guess you'd call it a curve of engaging the power. This one, by the way, the ones we have on our line, so everyone, I'm not sure about the stepping motor, but every one of our DC motors over there on the line has a slip clutch on it. And what we can do is we can change the tension by adjusting this adjuster. And basically it's just changing the tension between two plates that rub together, right? That makes sense? And what's nice about a slip clutch, if something actually stalls, especially if you got gears out there, if something stalls, then what would happen? The clutch would slip. So these are slip clutches. Are you okay? Any questions on these? This is a planetary gear. I wasn't, go ahead. Okay. These are what we call planetary gears, which is real neat. We don't have these over there, and I'm going to have to actually go in and look at these. There's a really good video about what the advantage of planetary gears, because you can change, if you change the driver and the driven, you get different speed multiplication, and that would be one of these guys. This was just in the slide, so I'd leave it over here. Your transmission uses a lot of what we call planetary gears. What it gives them the ability to do is we can clamp on one and release the other one. You have a reverse. If we clamp on one and drive the other one, you have forward. So when you shift between forward and reverse in your car, you're basically dealing with a planetary gear. So you're not really, because your motor is always turning into what? In the same direction. There's a good video I'll show you. It's tanks, and the guy explains it, but it's still kind of hard to comprehend. Well, let's look at chain drives. Everybody okay with chain drives? So what advantages chain drives have over gears? Well, the motion in the same direction. So what do we use idler gears for? We use idler gears and gears to make the driven and the driver run the same direction. But also, if I want to move these things apart, right? You understand? I'm going to move them apart. So my driver's over here, my driven's over there. Well, we can make the gears real big to maintain the ratio, or we can use idler gears of different sizes. Now, notice idler gears don't change the what? Don't change the speed, the ratio between the driver and the driven. So idler gears, we use those to increase the distance between the what? The driver and the driven. And also we use those to do what? To make the driver and the driven run in the same direction. So if I want them real close, then I use a small idler gear. If I want to move them apart, I can make the idler gear different, right? And we can use multiple idler gears. A chain drive, the driver and the driven run in the same direction. Plus, if I need to spread them out, I just use longer chains. So basically, the spacing between your driver and your driven can be literally any distance, right? You understand, as long as you maintain the slack in your chain, use rollers and tensioners and that kind of stuff. So the advantage, of course, is the transmission of high torque, low, and of course, one of the biggest advantages of these is these things are a lot cheaper than gears. Chains are a lot cheaper than gears. So some advantages, of course, is your driver and your driven running what? In the same direction, right? You understand that. Another advantage, of course, is the distance between the driver and the driven. Basically, it can be any distance as long as you can maintain or keep the slack out of the chain. These guys are relatively low to install. They're relatively available. Just about any gear you want, you can buy it online, buy it stock, or not gears. By the way, we don't call these gears anymore. What do you call them? Yeah, we refer to these as sprockets. And of course, the spacing between them, we call it the pitch. It's basically the length between this guy right here, between the pins on the chain. So these pins right here on the chain would be what we call pitch. That makes sense? This guy here is 90 to 95% efficient, installed correctly. Okay. Yeah, if, and this is the biggest problem. They say 15,000 hours of design life is properly maintained. The problem we have is very few people properly maintain it. So if you don't have your alignment right, they said, you know, if you don't do a real good job on your chains, that's looking at could be as low as 100 hours worth of use if you don't maintain it. Create chains of any length, which is really, really a good advantage. So your driver and your driven. The ratios, by the way, are exactly the same. We can use the sprocket teeth for our driver and our driven. Right? You'll understand that. Now the pitch of your driver and your driven has to be exactly the same. And that's also true on gear. Okay. Or we can use the circumference. Or we could use the radius. So this is true when we deal with any of these, except for belts. Belts don't normally have teeth unless it's a synchronous belt. So on belts we normally don't use teeth, but what can we use? We can use circumference to get our torque and speed. So the biggest problem we have with chains is this guy right here. People don't like to do what? Lubricate. And of course, alignment, just like gears, that's another thing we got to be careful with. Your gears have to be aligned correctly. So our sprockets have to be aligned correctly. If they're off, then what's going to happen is the chain's going to run on one side. And then what's going to happen, if your chain runs on one side, it's going to wear your teeth on your sprocket, and it's also going to wear your chain. So alignment is very critical on these things. Tension is very critical. You have to maintain a certain tension for the spring. If you get it too loose, then the gears could jump on your sprocket. If you get it too tight, it's going to wear it real fast. So keep maintaining the proper tension on your chain. And then, of course, the drive components. So these are chains. And chains also would transmit vibration. They're a lot like gears. By the way, they say, when do you change it? And I need to click on this. What you're supposed to do on your chains is you're supposed to come in and constantly check your pitch. And if your pitch changes, what you're supposed to do is 3% over their length. 3% manufacturers recommend that you replace the chain. And we'll see if this one plays. We'll see how our network is doing. Oh, I didn't want to do that, guys. We'll see if it plays. Our speed on our network is awful. So what I'll do is I'll find this one and download it to I'll do that when y'all gonna break and we'll come back and play them. So let's go ahead and look at belts. Now what would you think the big advantage of belts are? Yeah, the biggest advantage of belts are cost. And of course another big advantage is alignment is not real critical. We can use things called idler wheels to change the directions. We can, if we want the output to run, I don't know if y'all have ever seen it before. If we want the output to run in the reverse direction, we can cross the belt, go in between the driver and the driven, and that way the output will run in the opposite direction than the input, which is pretty neat. So belts are used a lot. So we have flat belts. They're not used much anymore. These were the predominant belts for a long, long time. Then we have what we call synchronous belts, where it's got, the belt is basically a flat belt, but the teeth in the thing are precisely spaced. Then we have the predominant belt, which we call the V-belt. I've ran into these before, probably. These are ones that you predominantly on your car. Of course, they're starting to use a lot of the timing belts too when you're familiar. Notch belts, these are a different version of V-belts. And of course, the advantage of notch belts is they last a lot longer. And of course, they run cooler because you can see these guys here actually carrying. Then we have what we call the poly V-belt, and these are basically just a bunch of these V-belts, but notice they're combined together. You see these a lot used on using smaller belts. Of course, when you deal with a V-belt, it wouldn't work real well if you spread it out over a big old belt, right? So what you're trying to do is you're trying to get real good power transfer. So we use multiple V-belts. Another advantage, of course, is that if one of your belts does break, then you might still be able to run the system and produce a V-belt. If you try to transmit more power than it's designed, the belt just slips. Okay. On a gear, something's going to happen. Right? A chain might break. And of course, if the chain breaks, you got that metal flying all over the place. And the same thing's true on gears too. If you shear a gear, then you got these chunks of metal that get into your gearbox. That's going to cause a cascade failure. That one played okay, didn't it?
Probably should have V-belt. Seen those?
What are the? Yeah, I saw that on a line somewhere.
Well, I mean, it's basically a V-belt, but they depending on the number of pulleys that you have on the system. Like we have a lot of pumps that were driven with 6-foot pulley. So the super belt laid all in one. So you didn't have like if there was slack, I have a job like that, you clean it up. The super V-belt was all in one.
Well, it was a group like this. It was a poly belt like this.
Pretty much.
Yeah.
They just call it the super V.
Now, the one advantage using just multiple V-belts is that if one of them breaks or something, you replace one belt. These guys right here will probably last longer, but the problem is if it breaks, the belts cost a lot more money. Also, we can get V-belts that are what we call a slip design, and a lot of riding lawnmowers do this, where they have a tensioner that actually applies tension. You let that off, and the belt itself can act like a clutch. And you see that a lot in riding lawnmowers. The older and the cheaper models. Of course, the notched V-belt, one of the things that he brought up that I forgot to is these things are a lot more flexible than these belts right here, which means you can take them around smaller pulleys, right? So in the distance that we put these things apart, they can be extremely long, and I needed to bring some more slides up here. We can use these to change direction. So if we want them to run the same direction, we just loop them. There's a lot that deals with the taut side and the slack side, so there's a lot to this. One of the things you got to understand is similar to chains. These guys are designed to run under a certain tension. So we have these tension gauges that we can use where we literally push in on the belt. Normally what we do is we take like a straight edge and put it between two of the pulleys. And then what we do is we come in and we push this thing down there, and it measures the amount of pressure we have to put on there to cause the belt to deflect a certain amount of inches. And of course that would be what we call a tension. So you need to maintain good distance. Good tension on these things. A lot of your riding lawnmowers have an automatic tensioner on it, where they'll run the belt up against something that's got a spring on it, and then the spring keeps basically the same tension until the belt is flat wore out or the belt breaks. So these guys they're real easy to mount. Normally all you have to do is you take the tension off of it, you wrap a new belt around there. So these guys, real fast, real cheaper maintenance. We don't have to lubricate them. We can run these things over great distances. We can use what they call idler pulleys, which don't change the speed or don't change the torque. But what they can do is they can actually literally change the direction.
Should get more than just like that.
Yeah.
pretty much sums up.
Of a mower, most of your new mowers, like the one I've got, uses clutches. So it's got a true clutch between the motor and the blades. So you can engage and disengage the
They don't have,
clutch.
they don't have belts on the actual deck.
Yeah, it does. It has belts on the deck, and then it's got the idler with the tensioner on it. It's got a spring on that. We had a Craftsman mower though that didn't have that, and it don't take long for the belts on most things to wear out. So I put a tensioner on it. I built one myself. Not the big one. We had a 24 horsepower, big old Craftsman, but it was a steering wheel drive. It wasn't a zero turn radius drive, and it had a proportional drive seemingly on it. But you have to transfer power. And what's nice if you got a riding lawnmower is that you can raise and lower the deck. And what happens is the bell just does what? Changes the angle, automatically changes the angle for you. You couldn't do that with a chain. Couldn't do that with a chain drive. Yeah, and your deck moves around all the time, but the belt has no problem with that. You just didn't. Like I said, I put one on there. I don't think this is the one, and we're not going to, I think this is the one. This is one of our guys that has, we have two belt drives over there that I think, and both of them use synchronous belts. And so we could calculate the ratio on both. One of them is to drive the ball and screw gear, and the other one is to drive the shuttle down the very end right there. We'll go and look at those in a minute.
Why, just out of curiosity, why is mechanics such an important part of this certification?
Because it's a mechatronics troubleshooting class. So mechatronics is a combination of mechanical and electronic.
Right, I mean, that's,
But if you go into automated, even down in Mercedes, they have they have change drives, they have belt drives. So that's what it is. It's trying to teach somebody to get prepared on what they'll run into in a mechatronics
okay,
system.
so the same certification that we're going for is going to be a mechatronics.
It is a mechatronics certificate.
Okay, I was under the impression it was a PLC.
No,
certification.
PLC is just a minor portion of it. So it's just one little portion, and you don't really have to know PLC programming to do the level one.
Okay.
So it's a mechatronics. So it's a lot like the guys down there that, at Mercedes that are, US Steel, I think, call them utility repairmen. They're the jack of all trades.
Right.
And what they're trying to do is and it's basically more on an operator level than it is on a maintenance level. Level one is where you got an operator out there that understands the system and knows how to transfer problems to the maintenance people and also knows how to do routine maintenance. Level two is going to be more complicated.
Okay.
So it is a mechatronics certification.
I was under the impression it was.
No, it's nothing to do. It's basically a PLC. It's mechatronics. And Siemens makes PLC, but Siemens makes drives. They make relays. They make all kind of stuff. It's just like Allen Bradley or Rockwell. Allen Bradley is just a section of Rockwell. Allen Bradley was bought by Rockwell. It used to be from its own. And Allen Bradley, the Allen Bradley name was so ingrained that they didn't change the name of that section of their company. So their PLCs are still called Allen Bradley PLCs.
Is ABB part of that? Has it ever been?
No, ABB is a company on its own. ABB don't make, Allen Bradley doesn't make, or Rockwell doesn't make robots as far as I know. And the Siemens don't make them as far as I know. You can never.
They don't make any, they service. There's Rockwell Automation.
This is a sample of a typical Siemens certification test. So it says the running noise in a belt is unusual. What is not the main cause?
Belt driving system's not lubricated.
So this has nothing to do with the belt, right? This is the one, the driving system. Aside from teaching and outer poles are used for some reason, which are not these reasons. Those
Maybe
reasons.
they throw a dot in there.
Yeah, now be careful. This said what? 2 answers. By the way, this had only 1 answer. So this is what I'm trying to do on our test, is try to tell you how many answers. Of course, I really don't need to do that because the software that we got will automatically, if I gave it 2 points, then that means it has 2 answers, right? You understand that? So let's see, so we're trying to find out, aside from tension, so these are called Euler pulleys. So we use them to tension, but we also can use them to change the direction.
Allow the belt to deliver instructions.
That's true. So we're trying to find out which are not those reasons. So C, so y'all agree with that? So pulleys don't do anything. Either pulleys don't do anything. What sets the torque? What sets the velocity and what sets the torque is the ratio between the driver and the driven. So this works just like an idler gear. It does not change the torque. It does not change the speed.
Increase the power or decrease the velocity.
Yeah, so it's not going to do what?
Increase the gravity.
It's not going to change the speed. Everybody understand that? So, huh?
I need to let them answer these. Hey, it's my cup of tea right here. It's all I need. You must do.
So this is what we went over. So noise levels, belt driven excess. It could be the tension of the belts is too high. I think that was in there. Contamination in the belt drive, edge wear on the belt, wear on tooth flank or of the belt, and fully out of the line. This is what these people came up with. And this was actually put out by Siemens in Berlin. Okay, guys, y'all go ahead and take a break, and then we'll come back and go over there and look at the mechanical things of the line over there. Yay! And there's a formula for calculating this, but basically, the bigger the number, the smaller the gauge. So we asked y'all to buy, what, 22 gauge wire. So 22 gauge wire has a mil solid. Now this is not the one I'm looking at because they don't tell us. This just tells us the size. Let me find it. Of course, you see I got 3 of them. But what this tells us is the resistance. This is copper wire, by the way. Aluminum would have more resistance, so this is copper wire. Nope, they don't tell us either. Let's try one. Okay, so this tells us ohms per 1,000 feet. So if I was to look at a 22 gauge wire, copper wire at 25 degrees centigrade, it has 16.14 ohms per 1,000 feet. Now, of course, what we're doing on a relay is so what we're doing on a relay is we have coils of wire. And then we wrap that around metal, right? Understand that? Now, what I'm doing when I fire this thing up is I'm putting maybe a plus and a minus. And of course, the lower the resistance, the more current we have. Okay. The only thing on a DC circuit, the only thing that's given me resistance is the resistance of the wire. That's it. You understand? So if I was to come out here, and on a 24 volt supply, and I used 1 inch of 22 gauge wire, it would probably have less than 1 ohm worth of resistance. So that means that would be a short circuit, right? You understand? So what am I going to do? Well, I got to do one of 2 things. What determines this would be the material. And then the second thing it does is the gauge, right? And the third thing is what? Length. So what we're trying to do is we're trying to get a real strong magnetic field. Now what determines the magnetic field is, number 1 would be the current that you put through the wire, and then number two would be the loops. So what I'm trying to do is I'm trying to get resistance. I want a pretty high R, so they'll give you the current. So let's say I'm putting this on 24 volts, and I want 5 milliamps worth of current flow. Okay, so I would say, okay, R would be equal to V over I. So what would that be? So that means I would need enough wire to drop what? 24 volts divided by 5 milliamps. So that means I need 4,800 ohms. Number 24 gauge wire only has 16 ohms per 1,000 feet. Right, you understand? So that means 16 ohms, I need what? That means I would need a ton of wire. So what do? Well, we decrease the gauge, but we've got to get the magnetic field. So we add more loops. Yeah, so what we do is we decrease the gauge, we add more loops. So that means in a DC coil, you've got thousands of little loops of very small gauge wire. And it's still going to build that magnetic field, and all that magnetic field comes up here. It's combining, right? You understand? So the more loops we have, every loop we have, the magnetic field combines. So what I would do is I'd use a really small gauge wire on a DC coil, and I would use a lot of loops. Well, the problem is if I come over here and turn that off, that magnetic field comes and it collapses back into the coil. Now, what determines the amount of EMF, voltage, not current, what determines the amount of voltage is the strength of the field, and 2, the number of loops, and then 3, the speed of the motion. So I'll open up this thing, turn it off real quick. That means the field's going to collapse real fast. We got thousands of loops of wire. This guy is going to produce an extremely high voltage, which would probably wipe out the output of your PLC. Now, if I put this in this pushes the magnetic field out. But what happens when I open the switch, this comes collapsing in, and it would produce a voltage in the opposite direction. That's why it's called a counter EMF. So what we do is we take a diode right here, and we forward bias it for the counter EMF. Now, it don't hurt anything because the dang wires got so much resistance, right? You understand? So we call this, some people call these flyback diodes, some people call them counter EMF diodes. But what you want to do is you want to make sure you put that thing opposite of the polarity. So that means when it goes plus and minus, it's reverse bias and it don't conduct. So this is a check valve, right? You understand? And then when the counter EMF comes up, it puts minus or plus at forward biases, and it basically just no counter EMF. So that means if this thing right here is left out, then what could happen? Well, those DC coils could pop the output of your PLC. So you notice all these coils. Now AC, we don't have to worry about this because AC has something called X of L, which is 2 pi FL. So that means an AC coil has very low opposition because it doesn't get its opposition from ohms, it gets its opposition from this right here. So that means we don't have to put flyback diodes on AC coils because the field's constantly contracting anyway. But these flyback diodes, we need to put these on any DC coils that we put on the PLC. That makes solenoids. So if you got a solenoid out there, you need to have that on. You can put them on the input of the PLC, but you notice on here, so if we take off one of those relays, because relays don't care what polarity you put on, because they generate a magnetic field. They're going to generate, but it does make a difference on how you put that thing on there according to the PLC, what the output, the way it's wired, right? You understand? So when you go over there, anytime you see any type something like this out there on a relay, you need to make sure that you document somewhere the polarity. Of course, how can you tell the polarity on these things? They got a dash, they got a little line on them. And this has to go toward the negative, and then this other side would go toward the positive. If you don't know that, then what you would do is you disconnect the wires, you take a meter and put it across the thing, you fire the thing up, and look at the polarity. And that's why, because if you put this thing on there backwards, then what happens? Well, if you put it on there backwards, you have a short circuit. So I don't know if they use different color wires over there or not. We probably need to put them there. So if I was to come up here and put it in there like that, then then you would have a short circuit. Now most PLC outputs are protected against that, so it probably won't cause any problems. The old PLC used to have fuses in the output boxes. You literally have to take it out and replace the fuse. So that's what those diodes are for. We should have told that, and I should add that to the electrical since they use that over here. Get y'all a little. So you understand a DC coil. You can't use a DC coil, a relay in a AC circuit because it would have a bunch of this, and it would never work. We're trying to order some relays for our motor control labs up there, and of course they sell them with 24-volt DC coils on them. But all they have to do is take the coils off and replace them with a 120-volt coil. So you okay? So we call these what? Some people call them flyback diodes. Some people call them counter EMF diodes. It don't make any difference as long as you. So we call that a flyback, right? When that thing collapses back, it causes a voltage to induce it. Are you okay? By the way, the amount of EMF you get has nothing to do with the gauge of the wire, because we're not dealing with current, we're dealing with a voltage that would be induced. And if we use a lot of turns of wire, then it has a pretty high R, right? You understand? So that when that diode forward biases, you'll never see a voltage because it's cut off instantly, and then the coil itself drops that counter EMF.